So we're now in the third video clip. So what did we do? We had the kinematics table. We found the velocity of P. We said that if the center of gravity is halfway up the length, then Vg is just simply making the r's over 2. Velocity of B was x dot I. So we said the Lagrangian is equal to kinetic energy minus potential energy. That's capital T minus capital V. The kinetic energy has two components, translational and rotational, and the potential energy has gravitational and elastic, and this problem only has gravitational. So we put it together and we have our L. So we said there are 2 degrees of freedom, and we want our equations in terms of that Q, X and theta, right? We want to know the forces that would drive that car, maybe the motor at on the link at pin B that creates a torque to move it. So what does that look like when we use that small q? So the Euler-Lagrange equation is our equation of motion. But that is the equivalent of your F equals ma, or your sum of the moments equals I alpha. That's what it's the equivalent of. So what do we have? Partial of L with respect to Q dot. Let me fix that. And maybe I have to move this up. Q dot. There we go. Time derivative minus partial L with respect to small q equals capital Q small q. So this here is my generalized coordinate. So in this case, x and theta. Why are we doing it this way? It allows us to put it in a computer and just iterate. If I have 2 degrees of freedom, I loop it twice. If I have 10 degrees of freedom, 10 times. Q dot would be a generalized velocity. So with this one here is x and theta. This would be an x dot and a theta dot. What's nice about this is a generalized force. So if small q is something that translates x, y, and r that changes with time, that capital Q would give you a force. If it's an angle, in our class we've been using theta, phi, and psi. For small q, that capital Q would automatically become a moment. So let's see what that looks like. So we have 2 degrees of freedom. And so here are our 2 equations of motion. Partial of L with respect to x dot, time derivative d dt, minus partial L with respect to x equals f of x. Right, capital Q, because x translates, becomes a force. Our second equation of motion is partial of L with respect to theta dot d dt minus partial L with respect to just theta. And because theta is an angle, that capital Q becomes a moment about theta. So these are our 2 EOMs, or equations of motion. So by just substituting in L, right, and having dotted this, our VG dotted with VG, is just some mindless derivatives to get our equation of motion. Now right now I'm not showing any particular forces or moments, so just temporarily this side would be 0. But as we started in class this week, we will solve this as well using virtual work.